Hi, everybody. My name is Charlie.
And I'm Savelli.
We work for Wells Fargo. We're software engineers on the advanced computing team. And today we're going to talk about how we implemented the fastest quantum state simulator with Rust, which we call Spinoza. All right, so just going to start with a little bit of context on why we made Spinoza. So why does Wells Fargo care about quantum computing? If you're familiar with the field, you might know we do not have large enough or fault-tolerant quantum computers that we can use in production within the bank. But our team exists because we want to, sorry, a little bit of an echo. Our team exists because we want to be ready when they are available. And so we want to be engaged early in working on solutions so that we can plug in and take off when the time does come. So what our team does is we look at opportunities within the bank or use cases where a quantum solution might be advantageous. So these are problems that are hard for classical computers, like large optimization problems, and also a couple of things that classical computers cannot do, like truly random sampling. So just a couple of examples here of things that areas of focus for our team and examples of applications. And then I also included here, we share a lot of our work. And so some of it is internal research, and some of it is joint development with IBM Quantum. We use their quantum computers in our research. So I just included a couple of titles from those papers. All right, so why do we need a simulator? So some quick definitions if you're not familiar with the field. So quantum computers are a different type of hardware, and it's the early stages of building quantum computers. And so the ones that are currently available are noisy with high readout errors. And so when we say simulate or simulator, we're using thanks to a whole bunch of physics and math, we are using what we know about what happens in a quantum computation and simulating that on classical hardware. So simulators are used to understand what results we would expect to get from a quantum computer. They can also be used to create noise correction methods to make results we currently get more useful. So secondly, development. There's more flexibility when you design an algorithm using a simulator. So oftentimes in our research, we use simulators and then we run those computations on quantum hardware as part of our process of development. But there are other uses for our simulators, like optimizing parameters for different models to be run on quantum computers, benchmarking, and also just education or learning. Simulating quantum computers on classical computers is a hard problem. And this makes sense because otherwise we wouldn't be so interested in quantum computers to begin with. But on a classical computer, we represent information with bits, of course. And so if we have n bits, we have n binary values to keep track of. On a quantum computer, information is encoded differently, where there's something called qubits. And for each qubit, so for n qubits, you have 2 to the n complex values that you have to keep track of. So this means that the complexity of simulating increases exponentially with the number of qubits that you want to simulate. So I'm going to try to paint a little bit of a better picture of this with a topic that comes up frequently in quantum computing, which is, can quantum computers break encryption, specifically RSA encryption? So RSA encryption depends on the fact that prime factorization is difficult when using classical methods. But there is an algorithm called Shor's that, when run on a quantum computer, can factor large numbers much, much faster. But you might be wondering, if you've never heard this before, you might be wondering why no one's panicking. And it's because we do not have quantum computers that are large enough to actually do this. The largest quantum computer right now is 433 qubits. It's an IBM quantum machine called Osprey. So right now, researchers estimate we would need about 1 million qubits to crack RSA. As I said, we're at 433, right? That's not enough. So if I just said we can simulate quantum computations, why can't we just simulate Shor's? So if we need 1 million qubits, we need to represent 2 to the power of 1 million complex numbers. The classical bits required to represent a complex number is 128 bits. So to give us a little bit of perspective, the number of atoms in the observable universe is approximately 10 to the power of 80, or 2 to the power of 266. So to simulate 1 million qubits, we would need more bits than there are atoms in the observable universe. So this is just to paint a picture of how massive or how difficult it is to simulate these computations. So what can we simulate? So imagine we have access to a very large system, a supercomputer. This one is the Frontier Oak Ridge National Laboratory. It has 9,472 nodes with each with a CPU and 4 terabytes of memory. So we just did a little calculation. If we divide the work evenly, we could simulate approximately 51 qubits. So once again, not enough to simulate Shor's at a meaningful scale. All right, so before we get into the implementation of Spinoza, I'm going to attempt to explain some of the essential concepts of what happens in a quantum computation. I am not a physicist, and I'm going to attempt to do this without referencing any physics. So I apologize to the physicists in the audience if this explanation is underwhelming for them, but I hope that it helps. So first thing, before we get into it, complex numbers. You've maybe never seen one or forgotten when you did learn about them, but we have a number with a real part and an imaginary part. For the sake of Spinoza, what you need to know is that we just need to keep track of those two values, right? The real value and the imaginary value. So you can even think a point on an XY grid, right? So in this case, we would have 2 and 4. So when we represent these in Rust, we have a struct with 2 64-bit floating point numbers, one for the real value, one for the imaginary value. So this is where I get that, or this is where that 128-bit number comes from that I mentioned before. All right, so I'm going to give a very simplified example to help explain a really important concept called quantum parallelism. So just imagine I have a list of 8 values that correspond to some attributes. So you could imagine these are distribution of scores on a test, distribution of probabilities of some event or occurrence. So we just have 8 values in a list. So if I encode my list in a classical computer and then I want to perform some operation on it, say I want to swap pairs of values that are next to each other, so those corresponding to the indices 0 and 1, 2 and 3, and so on. In a classical computer, and I'm oversimplifying, I know there are better ways to do this with smaller values like this, but I'm going to maybe write a for loop, and then it's going to give instructions to the machine sequentially, right? And I'm going to have to perform those operations sequentially. So imagine this list is millions of values or longer. This is going to get harder and harder for a classical computer. On a quantum computer, I have something called quantum parallelism, which means with one gate, I can swap all of those values. I can also perform other operations with just one instruction, but this is an example. This would be an X gate applied to a certain qubit. So one instruction, I can swap all the values. And so this is true as the size of the system increases. So once again, if you imagine we have millions of values, it's still only one instruction that I need to change all 2 to the n values in my state. So what do I mean by in my state? So on a classical computer, we have bits, we have binary values. On a quantum computer, we have qubits. And when we encode information in qubits, we have for n qubits, we encode information in the amplitudes of those qubits, and there are 2 to the n amplitudes. And we can represent amplitudes with complex numbers, once again, thanks to the laws of physics. And so when we want to encode in our simulator, we want to classically encode the state of n qubits. We need to have 2 to the n complex numbers. And so imagine here if I have 3 qubits, I'm going to have 8 complex numbers. So I'm just going to have the vector of those values, and that's what we call the state or the state vector. All right, so then changing those values. So I'm going to, in a quantum computation, I have a series of operations that I want to change my state with, change the amplitudes of my state. So you will find that these are represented by large matrices. This is an example. This would be applying an RY gate to target qubit 0 in my 3-qubit state. So if I try to, as my system gets larger than 3 qubits, if I have to do this large matrix multiplication, classically, that's going to get not pretty. And so in our simulator, we use a strategy we called pairs, which is so to avoid allocating those huge matrices, we utilize the fact that all quantum operations can be broken down into basic quantum gates, which can be represented by a 2x2 matrix. So we have 4 values. These can be real or complex that define the gate. And then the gate is applied to one target qubit in the system, so one of my n qubits. Okay, last thing I promised that you need to know. So I just told you there are n qubits and I have 2 to the n amplitudes, right? On a quantum computer, I can't actually read or write those amplitudes during the computation. All I get is what's called a measurement outcome, and that measurement outcome is a binary outcome, and those amplitudes determine the probability of that outcome. So when I apply gates, I'm changing my amplitudes because I want to change the chances that upon measurement I get different values. So there is a method to the madness, but we're not talking about writing quantum algorithms today. What you need to know is that for my n qubits, I have 2 to the n possible binary outcomes, right? So if I have 2 qubits, those are my 4 possible outcomes. For 3 qubits, my 8 possible outcomes, and so on. So back to my state vector. Each amplitude corresponds to one of those outcomes. So you can see here for a 3-qubit state, these are my possible outcomes. And the index, so if we interpret that binary outcome as a positive integer, it will match the index of the amplitude. So 0, 0, 0 is 0, and so on. So that amplitude, that complex number, determines my probability of getting that binary string when I measure. When we run quantum computations, we run them many, many times, and we look at the frequency of outcomes, but you just need to think about one measurement for now. All right, so how do we find our pairs? So as I said, we're gonna have a target qubit T. Qubits are indexed from the right. That's a convention in quantum computing. So if I have 3 qubits and I apply my gate to target qubit 0, that the measurement outcome of that qubit is going to correspond to my rightmost digit, and then my pairs are going to be the amplitudes which correspond to the outcomes that differ only in that position. So 0, 0, 0 and 0, 0, 1, they differ only in position 0. And then, of course, that's how I find my corresponding amplitude, which is that complex number. So another example, if I have 4 qubits and I apply a gate to target qubit 1, these will be my pairs. So you'll see they differ indexing from the right. They differ only in that position, and these help me identify the corresponding amplitude that I want to change. So when we simulate a gate application, what we do is we have our definition of the gate. We have those 4 values, and then we have the target qubit. There can be control qubits, but we won't talk about that today. And so what happens is we need to identify the pairs. That tells us where our amplitudes are that we need to find. And then our 2x2 matrix tells us how we're going to calculate the new amplitudes. So you'll see here, if I have a 3 qubit state, target qubit 1. So let's just look at one of my pairs, Z0 and Z2. Once I find those, I can take them, recombine them. What we call recombining or processing amplitudes is when we do that step, the computation. And then we update the values in our state vector. So this pairing strategy allows us to do this in pairs rather than one of those very large matrices like you saw a couple of slides ago. And Saveli can take it from here.
Thank you, Charlie. So I guess let's consider how we can generate these binary strings that Charlie mentioned. And here in this case, we call this strategy insertion. So we're going to be inserting into the target position. So we start with a prefix where we choose between 0 and 1. We choose a suffix, and again, we choose between 0 and 1. And finally, we insert the target into its respective position. So in this case, the target is 1. So for the 0 side of the pair, which I just mean by this left side here, we insert a 0 into position 1, right? And then the 1 side of the pair, we insert a 1 into position 1. And that's pretty much it. So how does this actually look? Let's take a look at the code snippet. So here we have the distance is just how far apart the pairs are from one another. So, and namely, the distance is always 2 to the target power. The number of pairs is always going to be the length of the state vector divided by 2. And finally, we generate the index of the pairs, which are S0 for the 0 side and S1 for the 1 side. And if this code snippet looks like gibberish to you, the important takeaway from this snippet is that in order to recombine a pair of amplitudes, we must first find the positions or indices in the state vector by generating S0 and S1. And now let's visualize this strategy. So we begin with a state vector for a system with 4 qubits. Hence, we have 2 to the 4th equals 16 elements in our state. And the distance is always 2 to the target, and 2 to the 0 is equal to 1. So the distance is 1. And as we can see here, the pairs are all 1 element apart. Now our target is 1, so the distance between pairs is just 2. And next, our target is 2, so our distance between pairs is 4. And finally, our target is 3, so our distance between pairs is 2 to the 3rd equals 8, and that's pretty much it. But before we actually look at the generated assembly of that code snippet, let's just take a little detour and discuss SIMD. So, in general, if we want to add 2 numbers together, right, the CPU fetches the add instruction and adds the 2 registers on which the data exists, right? Hence, single instruction, single data. But modern CPUs come with instruction set extensions that allow us to execute a single instruction on multiple data simultaneously, right? Hence, single instruction, multiple data, or SIMD. So for example, we can add 2 registers that each contain 4 64-bit values, and then we just get the 4 64-bit values as an output. So depending on the CPU, a programmer may have vectors of different sizes available. Here, in the case of 128-bit vectors, you can either process 4 32-bit elements at a time, or you can process 2 64-bit elements at a time. And similarly, if your CPU makes 256-bit vectors available to you, you can either process 8 32-bit elements or 4 64-bit elements at a time. I know that some modern CPUs have 512-bit vectors, but we're just going to skip that for today. So with that being said, let's take a look at the output of our insertion strategy. So here we see a variety of instructions, but the main takeaway here is that you see this XMM, and that XMM register is just generally associated with 128-bit vectors. So you're probably wondering, why should I even care? Okay, so for most of this work, we utilized a C2 standard 16 machine on Google Cloud. And so on that machine, we should be able to at least utilize AVX or AVX2 instruction set extensions, which give us access to 256-bit vectors. So are we utilizing the best instruction set extension available to us? Sadly, no. So let's consider how we can resolve this issue. But before we can do this, we need to dive into SIMD just a bit more. So the 3 levels of understanding how SIMD works. Compilers are smart. They're capable of producing exceptionally optimal scalar code. And let's not get too arrogant and assume the compiler won't do the same for us when it comes to vectorized code. Okay, well next, compilers are dumb. It's always better to manually write explicit SIMD, right? Auto-vectorization is held together by hopes and dreams, so let's bite the bullet, write some manual SIMD. Well, maybe not. So writing manual SIMD is really meticulous work. You may need to redo the implementation for various CPU architectures, as well as the precision of your elements. How about we just help the compiler realize that code is able to be vectorized, and the compiler will return us the favor by outputting clean and performing SIMD for us. And you may notice this amenable to vectorization term here, but what does that actually mean? So in general, we want to process chunks of elements at a time, and we want to process each chunk in a similar fashion. Well, in the case of applying gates to a state vector, where are these chunks, right? Well, recall our state vector where we have 4 qubits for a system of 4 qubits, and our target qubit is 1. Well, take a look here. We can see that we actually have 4 chunks here. And now we can discuss the next strategy. So let's see how concatenation works. So we start with a prefix. Again, we choose between 0 or 1. Next, we append the target, 0 or 1. And finally, append this suffix, 0 or 1. Okay, so let's take a look at the snippet here. And again, similar to the insertion strategy, the takeaway here, if this looks like complete gibberish, is that in order to recombine a pair of amplitudes, you must first find their indices in the state vector by generating S0 and S1. But let's now visualize the strategy as it's actually applied to our state. So again, we begin with a state vector for 4 qubits, so we have 16 elements in our state. Well, in general, the number of chunks is going to be the length of the state divided by 2 to the target plus 1. So in this case, we have 8 chunks. Next, for the first, if you make the target qubit 1, well, you're just going to have your number of chunks is going to be 4. And next, for target qubit 2, well, the number of chunks you're going to have is 2. And lastly, if you have target qubit 3, you just have 1 giant chunk. And now let's just take a look at the actual assembly given to us by the compiler. So this might look, again, like a bunch of gibberish, but if you notice here, some of these instructions have shuffle in it or something that looks like permute. The important thing to note here is that to execute permutations, it's quite costly. And unfortunately for us, there's a lot of those instructions here. So takeaway here is SIMD isn't always simple, and it may leave us at the mercy of our memory layout. So let's go back to the drawing board. So our implementation thus far has been we have a vector of structs, namely a vector of complex numbers. And you've all seen this quite a few times already, so here it is. And underneath what it actually looks like, right, as Charlie mentioned, it's just 2 values you can think of like XY coordinates on a 2D grid, right? So that's all it is, A0, B0, A1, B1, etc. Okay. So how about we split the components of our struct into the real and imaginary components, and hence we can switch our layout from a vector of structs to a struct of arrays. And specifically what I mean here is as follows. And that's all. We just have two vectors right there. And now, here's the corresponding snippet that in Rust, and that's pretty much it. So let's again recall that code snippet for the concatenation strategy. There's nothing different here whatsoever. It's the same as the one we showed before, but let's look at the outputted assembly. And now notice how the instructions listed here for the same strategy are much cleaner. Namely, they're mostly just arithmetic in nature. You have a bunch of multiply, subtract. The moves are obviously, you can't get away from those because you need to fetch the data. But other than that, it is much cleaner. And modern CPUs are great at crunching through these type of instructions. So maybe we can do even better. But let's consider our bottlenecks here. So recall the state when we have 4 qubits and the target qubit is, for example, 3. Excuse me. So now consider when the number of qubits, for example, is 26 and your target qubit is 25, right? Well, let's see what it would look like to get a pair. Well, they would be quite far apart in memory. As a matter of fact, the distance between each side of a pair is over 33 million elements. Now, on modern machines, memory is relatively cheap, but it can take hundreds of cycles for a CPU to receive requested data. So to bridge this gap, a layer of caches is used, namely L1, L2, L3, where each layer is available at a decreasing speed and cost. If the CPU can't find the data in the L1 cache, then it looks in L2. If it's not in the L2, then L3. And in the worst case, it goes to main memory. And each of these misses is expensive in time. So here we can see the cost of accessing data in various levels of memory. Note how accessing data in L2 is 14 times as expensive as L1. Main memory access is 20 times as expensive as access something in L2, and 200 times as expensive as L1. So consider the cache misses as the number of qubits grows and as the target qubit increases in size. And as you can see here, our benchmark machine on the left, that's its architecture. So it's quite easy to overcome the space of the cache, which just leads to an egregious amount of cache misses. So can we do any better? Well, certain gates, as Charlie spoke about, they can be special. You don't need to grab both sides of the pair. You can just scale you would consider each side of the pair individually. And there's technically no recombining done. So this leads us to our next strategy, group and traverse. So consider your blue elements. Consider your blue elements as ones that are going to be multiplied by some value x, and the pink elements that are going to be multiplied by some value y. And then all you need to do here is that you have your chunk size of 1, you go through each chunk, multiply each chunk by its corresponding value, that's its corresponding scaling value, and that's all. And then the chunk size is 2, and next, for target qubit 2, the chunk size is 4, and lastly, for target qubit 3, the chunk size is 2. Now, you can see here that this is just a sequential access pattern, and we just iterate through this entire array, or through each chunk, until all the elements are scaled. And this is much more amenable and cache-friendly. And here we have the implementation of group and traverse. Now, I personally am I really love this implementation because it's, to me, really beautiful. You don't have, you're just able to completely use iterators. And of course, there's no bounds checking or anything. But even more beautiful is when you look at the outputted assembly. It is just completely nothing but almost arithmetic operations that CPUs just love crunching through. And Charlie.
All right. So just to wrap it up, as we talked about in the beginning, our intention with writing Spinoza was to have a simulator that we could use that was efficient and easy to work with. And so at the end of writing Spinoza, we put a Python wrapper on it, Pio3, because we wanted to compare to other simulators that were written in mostly C++, and also had Python interfaces, and compare. So these are some single-threaded benchmarks. We are working on more benchmarking as we go along, but as you can see, writing Spinoza and Rust really helped us make it the fastest. So a couple people that we would like to give a shout out to for helping us along the way. And you can find Spinoza on GitHub if you want to check it out. Open to your comments and thoughts. So thank you.